Good morning. So we are on lecture 23 today, and I want to point out some things I've assigned. So like I mentioned in the Piazza message, I'm swapping quiz 6 and blog 3. So blog post 3 is due this weekend, as usual at 23:55. So just to make things a little different, this time I've assigned a paper for the reading assignment and asked you to write your perspective on that paper. I think it will be an interesting paper. I've not tried this before, but the way I've set it up is I believe you'll be able to, you need to post your blog to be able to see other people's blogs that have been already posted and that will be posted. I think that's how it will work. But let me know if some things are not correctly set up. Okay, and then quiz 6 anticipated. I think we'll be okay for this for next Sunday. At 23:55, this will be the due date. And I've also posted project 2, which is on cambered airfoil design. And this is due Friday, last day of classes. I think it is 1st of November, right? Sorry? December. Is it December 31st? No, 1st December. Oh yeah, 1st December. Okay. We'll talk some more about project 2 in the next class. I want to make some progress on the thin airfoil theory stuff, or the background material for that. Any questions? How was project 1? So it's very open-ended, right? So there is no one way to do things or one correct answer, of course. So hopefully that was, and that's how real design is. Even at the end of it, you don't know if you have sometimes done it to the, to the maximum possible extent or not. Okay. Moving on. So in the last class, we were talking about the second elementary flow, which is a source or a sink. And this is radial flow everywhere. And this is the VR and V theta. So we'll continue from there and see what this looks like. And then we'll start adding some flows very soon. So strength. So velocity potential. So phi is velocity potential, and that is lambda over 2 pi natural logarithm of r, and psi equals stream function is lambda over 2 pi times theta. So you can see constant theta will be a radial line, and that's the stream function, or that will be a streamline, and constant r will be a circular contour, and that will be a constant velocity potential line. And it turns out that volume flow rate out of the source, this will be per unit distance in Z, is simply lambda. So the source strength has got a physical significance. Okay, so now we are going to combine the two flows that we have talked about, uniform flow and source. So flow 2B, number 2B is combination of uniform flow and source. Okay, so we have uniform flow is one elementary flow, and to that we are adding source, and we get a flow like this. So here's the source, and okay, so if you just add the stream function due to uniform flow and source and draw constant values of the stream function, which will be streamlines, you get a flow like this. Now remember, we talked about how any function that satisfies the last class we talked about two important points, right? And number 2 was any solution to Laplace's equation can represent the phi or psi for some irrotational incompressible flow. So that's, we're going to draw on that and say, and also the wall boundary condition is met by every streamline, right? Every streamline satisfies the same boundary conditions that are needed for a wall. So you can actually take this streamline and consider that as a wall and replace this as a solid body. So this outside flow represents the flow past some kind of a parabolic nose body of infinite, it goes to infinity in the rear, but the nose of it is like a parabola or some sort of an elliptical shaped leading edge, let's say. And so this represents the flow past a body like this. So one way to think about it sometimes is to say, if you want to focus on the leading edge flow of a symmetric airfoil, and if you zoom in and try to look at what the flow there looks like, this could be one possible model for that. So the stream function is V infinity r sine theta. So I'm converting, I believe this is y. V infinity y is the stream function for a uniform flow. Yeah, when we looked at it last time, stream function is u times y, right? If there is only a horizontal force, horizontal flow u, so that's u infinity y, and y is in polar coordinates is r sine theta plus lambda over 2 pi theta. So this is the uniform flow, and this is the source term. So we are adding up stream functions of two flows here because they both satisfy Laplace's equation, and that allows you to do such things. Okay, let's do one more combination. Combination of source and another source. So here we'll put a source here, and we'll put another source here. So we'll add these two flows up. Any quick guesses on what we'll get? Yeah, so this will actually become a streamline. So you will have a streamline like this, and this source will create a flow that looks like this. So one of the things you'll find is that this the line bisecting the line joining the two sources, or the perpendicular line in between the two sources, that becomes a streamline of the flow. And you can take any streamline and replace it with a wall, and the boundary conditions are satisfied. So you can actually take you can take this part as a you can convert this to a solid boundary. That means this part is, you can convert it to some sort of fictitious flow. So that means if you want to model the flow due to a source, but not a source in isolation, but a source near a wall, the way to model that is, it's hard to model a wall, right? How do you somehow figure out a wall? Instead, you can say a source near a wall is the same as a source with another source on the mirror side of the wall, right? And that resulting flow, if you discard the bottom half of it, this is the flow due to a source near a wall. And this general idea is actually really useful in so many places. So this gives rise to the idea of the concept of a mirror image Okay, so for example, sometimes airfoils operate very close to the ground. Can you think of an example where that happens? An airfoil that operates close to the ground. What's that? Takeoff or landing. Even more extreme. Yeah, cars. The front wings of cars are actually so close to the ground that the ground plays a big influence. It's like if you don't consider the ground, you're completely off on the aerodynamics. So you might have an airfoil that's like this, high lift airfoil. Now, how do you simulate the flow due to an airfoil near the ground? Because you can't ignore the ground, you'll be completely off. So one way to do that is to say, I won't simulate the ground. Instead, I will put a mirror airfoil under the ground. It'll be an exact mirror image like this. And I'll simulate the flow past two airfoils that look like this. So this is almost like a channel type of flow, right? So this part is really fictitious. It's not like there is an airfoil under the ground. But by putting two airfoils under the ground for simulation purposes, the ground becomes a streamline, and so the flow pattern on the top side of it is the flow pattern for the airfoil near the ground. In fact, you can do this even in wind tunnel testing. For some reason, if you want to simulate the flow for an airfoil near the floor, you can put it near the floor in a wind tunnel. You might have some, maybe for some unknown reason, if you don't want to do that, you could actually put two airfoils in mirror image formation, and the flow past the top airfoil is the flow past the wing or the airfoil near the ground. You can even do this all the way for like an airplane. So if you want to simulate an airplane in takeoff or landing, so let's say you have an airplane like this. That will be, to simulate that, you can instead put a mirror image and do the analysis past two airplane bodies, and the top one will be the solution for the airplane near the ground. Okay, let's do source plus sink. So you have a source and a sink placed close to each other, and the resulting flow will be, can you think of what it will look like? Not yet. Not quite an oval yet, or we're getting to that. But this will look more like a magnetic field due to, a bar magnet. Yeah, it'll look like something like that. Maybe not perfectly like that, but it'll be. Now we add free stream. Okay, so we have, to this we add a free stream. There's a source, and there's a sink. And what does this give? Now it will give an oval, right? So this doesn't tell us that this is flow past an oval. This is only saying these are the streamlines. What you then say is, I can take any streamline, especially a closed streamline. It makes sense to make it a solid wall. That means this streamline, if you take that as the solid wall, then you can ignore the flow inside. There's nothing wrong with the flow inside except that we are ignoring it and saying, hey, this is the flow past this oval shape. And this oval is called Rankine oval. I think it's the same Rankine who came up with that temperature scale. I believe, I'm not sure, but so that that's the outside flow is something that we can make use of. Now we'll go to the third kind of flow, which is a doublet. Here we take a source and a sink. And let's consider them at some distance L. But we are going to consider a limiting case. So we are going to bring these close to each other. So limit as L goes towards 0, but in the process we want to keep lambda times L equals constant. So it's not like you bring them on top of each other and the source cancels the sink. It's more like you bring them closer and closer to each other while maintaining lambda L constant. And this constant is related to the doublet strength. Okay, so doublet strength is denoted by kappa. And the stream function due to a doublet is minus kappa over 2 pi sine theta over r. And velocity potential is kappa over 2 pi cosine theta over r. So this is stream function and this is velocity potential. So you can take these functions and plot them in MATLAB or something. Just out of curiosity, go ahead and do it sometime and you'll see all of these shapes that we are talking about. And the nice thing is you can add these functions up, right? You can add these functions up and then go make a contour plot in MATLAB. There are some tricks to it because these are singularities, right? Right at the doublet, things won't work, but outside everywhere it should work. So the flow will look like this. So here is a doublet. The doublet has a direction. And so it has magnitude, which we've already seen, and a direction that points from sink to source. So this is the direction of the doublet, and the streamlines, anybody know or want to guess?
Sort of like the source and the sink, but forms a circle.
Yeah, so it's like this, right? You're squishing these things and bringing them to one point. So did he say circle? Yeah, so they're going to be in perfect circles like this. Okay, now we'll add a doublet and a uniform flow. This is probably familiar or should really ring a bell to many of you. So we have uniform flow like this, plus a doublet, which I'm denoting in this manner. What do we get? Yeah, flow past a circular cylinder. So if you draw these streamlines, and you can do this, you can just add up this stream function, and you'll get, stream function is V infinity r sine theta minus kappa over 2 pi sine theta over r. And so this is the set of contours of constant stream function. So these are the streamlines, and as always we can take any contour, especially it makes sense to take a closed contour like this and say, okay, let me replace that streamline with a solid wall. That means you can ignore the solution of the stream function plot inside this solid wall. It turns out that this is a circular cylinder or circle shape. So all of the cylinder, because it's a 2D flow, right? So it goes to infinity inside the page and outside the page. So this is a cross section. And so this becomes the flow past a circular cylinder. So this is the potential flow. And you can do other things too. For example, you could not only replace this as a wall, but even the horizontal surface, right? So if you want to simulate the flow past a bump, like a half semicircular cylinder with a wall, this top flow is the flow past a wall with a semicircular bump, something like that. Or you could say, let me replace one of these streamlines by a wall. So let's see how that looks. So let me take that picture, and so we said this flow is possible, right? You could also say, let me take a streamline like this, and let's replace that with a wall. So suppose you say that. This becomes a flow past some kind of a hill. If you wanted to, I mean, you'll be constrained to this exact shape, but if you wanted to get a flow past a gentle hill, potential flow, this is not real flow, but still it's useful sometimes. And one of the things people have talked about this for is when you go flying sailplanes, people do something called ridge soaring, right? So if you fly a sailplane near a hill on the upwind side, you get wind pattern like this. So the wind goes up. So if you fly a sailplane here, if you fly a sailplane here, the updraft, depending on how big the hill is, the updraft will cancel out your glide slope and you'll actually fly level. So without an engine, you can fly level. And if you have a long hill, if there's a big long range, mountain range, you can fly for thousands of kilometers along the mountain range without an engine, without losing altitude. And people have done that. They've broken records and done all kinds of things. So this is, if you want a simple model of, say, flow past some kind of a hill shape, this will give you. And one of the things this tells us is somewhere here is the zone for best updraft. I guess the point is you can take any streamline, replace it, take that as a solid wall, and that gives you the flow past that wall. Okay, so this is the flow past us. This is the solution that we use often. So radius of the cylinder is square root of, and I'm skipping a lot of steps which we do in the undergrad aero class. This is just sort of a review of those concepts, and if you haven't done this in some course, you may want to go and read up the stuff. Okay, so the big thing to remember here is this is ideal flow or potential flow. So in potential flow, the cylinder, so this is ideal flow, and let's say this is real flow. So in potential flow, you will have and you might have suction here. I'm not drawing this correctly, but basically forces cancel out in x and y directions, which means there is no lift and no drag. You can see even the flow is pretty symmetric, right? So there is left-right symmetry and there's top-down, top-bottom symmetry. So there's going to be equal and opposite pressures everywhere, they'll cancel. But a real flow is not like this. A real flow will have separation. Something of this sort. It depends on the Reynolds number. So you might have a wake where there's separated flow. So here lift may be 0. But separated flow so it results in significant drag. What kind of drag will that be? Pressure drag. Because you will have positive pressure on the front surface, but you'll have lower pressure in the wake, and so there will be pressure drag. And at many Reynolds numbers, there will be vortex shedding. So in many cases, you'll have flow behind a cylinder, and many bluff bodies will look like this. You'll have alternate shedding of vortices from the two sides. They'll keep flipping. This will come and then this will happen. So this is called a Kármán vortex treat. It's named after Theodor von Kármán, who actually explained and discovered this phenomenon. I think I have put one book as a suggested reading in the syllabus, right? It's by Theodor von Kármán. What's the name of that book?
Selected topics.
Yeah, selected topics in
Light of the historical.
Yeah, I think there's a precursor to that. Aerodynamics at selected topics in light of historical development. So there he talks about, it's very interesting reading. It's not at all like super heavy math and technical. It's story basically. And he talks about how he came up with this. Theodor von Kármán was a student of Prandtl. Prandtl was the guy who came up with boundary layer theory, lifting line theory, and those things. So, and this has also got a lot of practical applications, and one of the famous examples is the Tacoma Narrows Bridge, about which there's even a YouTube video. So you can see how the bridge, under certain wind conditions, it started oscillating so much that it just fell apart, and that's traced to vortex shedding. The other reason to study stuff like this, so you can almost ask, right, what's the point in, if the real flow is like this, okay, so that's real flow, that's what happens in reality. What's the point in studying flows like this? I mean, maybe mathematicians will find it interesting. Why should we waste our time as engineers on some abstract concept like that? One reason is that potential flows around cylinders, circular and even other kind of cylinders, are useful in conformal mapping. So in conformal mapping, what you do is you take flow around some kind of a cylinder, which is, this kind of flow is really well known. We have just written the equation for this. You can just add the stream function due to uniform flow and double it, and that's it. You get the streamlines due to flow around a cylinder, right? So you have this. This is potential flow, so it's not real flow. And the isopotential lines will look like this. They'll always be perpendicular to the streamlines at every point of intersection. So there is something called conformal mapping with which you can transform this. And when you transform it, you can transform it to an airfoil shape. And that's just kind of mind-blowing. So you can convert this flow by using a transformation function using complex variables, and this very well-known flow can be transformed to flow past some really complicated looking airfoil shape like this. Think of it, this is a really weird shape, right? It's nothing regular about it. I mean, we are so used to airfoils that we say, okay, that's a nice shape. But if somebody in the very beginning, 200 years back, if somebody wanted to calculate flow past this, nobody knew how to do that. And then they came up with conformal mapping, and we'll be talking a little bit about that in Joukowsky transformation. I mean, the way the semester is going, I'm very much behind, but hopefully that'll happen. So what happens is all of these streamlines get morphed into streamlines like this because of the transformation function, and this geometry gets morphed into this geometry, and the isopotential lines will become something like this. I don't know how they'll look, but maybe something like this. So that's a really good reason to actually study these kind of flows, even though they are very different from real flows. The reason potential flow past these kind of bodies is useful is why? Okay, this at least we can say this potential flow is nothing like reality because there's a big wake. But this potential flow is actually very useful. It's close to reality, but what? Yeah, these are streamlined objects. For streamlined objects, as long as angle of attack is small, the boundary layer is thin and attached most of the time all the way to the trailing edge. And so the potential flow is actually very close to the real flow. And lift and pitching moment at least you can get very confidently, even with angle of attack, up to 10 degrees or something. It's only drag, of course, potential flow has no drag. So for drag you have to do a boundary layer calculation. Okay, pressing on. Fourth elementary flow. Is a vortex. So a vortex is a flow where the streamlines are circular, concentric circles. And the sign convention in aerodynamics positive vortex results in in clockwise flow. And this is kind of counterintuitive because usually theta, in polar coordinates, theta increases this way, right? But this is somehow the way things are, at least in modern books like Anderson's books. So the velocity variation, so there's only tangential velocity and that varies in a certain way. So you have tangential velocity and that varies like this. So as you go up in y or in r, velocity decreases. And as you come closer and closer to the vortex, velocity becomes very high and actually goes to infinity. So in other words, so these are the streamlines. So v theta equals minus gamma over 2 pi r, and Vr equals 0. So there is no radial velocity. Okay, so strength of the vortex, where strength of the vortex is denoted by gamma. Which is, this is capital gamma. How do you think the isopotential lines will look for a vortex? Yeah, it'll be radial because everywhere isopotential lines have to intersect streamlines in a perpendicular fashion, right? So these are isopotential lines. Okay, so velocity potential is given by gamma over 2 pi times theta, and stream function is given by gamma over 2 pi natural logarithm of r. And in a vortex, curl of V, remember curl V is has to be 0 for irrotational flow, right? Potential flow is irrotational incompressible. So curl V is 0 everywhere except at the vortex point, and usually you put that at the origin. So except at vortex point, and this vortex point is a singularity. So just like in a source, conservation of mass works everywhere except at the source, right? So that point is a singularity. Like that, a vortex is also a singularity, and here curl V will not be 0. Everywhere else it will be 0. Okay, so this actually brings us to the concept of circulation. So circulation is the line integral So by definition, it's the line integral of the velocity field around a closed contour. So this is like a definition, so we just take it as they have defined. So if you want to write it in mathematical terms, this is integral v dot dl around a closed contour. Okay, so for a closed contour around a vortex, which means let's say that you have a vortex here of strength gamma, and then you make a contour like this. Yeah, so let's say you go in the clockwise direction. What do you think you'll get for circulation? It'll be equal to the vortex strength. So the circulation is equal to the vortex strength, and that's equal to gamma. So I think I should mention that circulation is positive for clockwise direction. That means you do the line integral in the clockwise direction. Again, this is opposite to what you will do in math. In the math, you'll do in positive polar coordinates, right? That will be in counterclockwise. So because circulation, which is completely mathematical definition, it's integral v dot dl around a closed contour. That turns out to be equal to vortex strength. So gamma is also is the symbol that's also used for circulation. So the circulation strength is denoted by symbol gamma, same symbol that's used for a vortex. So some nice consequences or connections between circulation and vortex strength. So if you take a contour around a single vortex of strength gamma, integral v dot dl equals gamma, right? So if you have a bunch of vortices, something like this, and this is, let's say, gamma 1, this is gamma 2, and this is gamma 3, and you take a contour like this around these three vortices, then integral v dot dl around this contour will just be sum of these vortices, gamma 1 plus gamma 2 plus gamma 3. So that just comes from just the math will turn out to be like that. Okay. So we are very soon going to connect all this with airfoil flows. Okay, now we'll go and add the cylinder flow we got earlier, and we'll put a vortex on top of that. So this will become lifting flow past a circular cylinder. So here you have uniform flow plus a doublet, which we had earlier, plus now we'll add a vortex at the same place where the doublet is, and we'll get lifting flow past a circular cylinder. And so when you do that, you'll So let's say we put the doublet here and the vortex here. Right, so you will get a flow whose streamlines are like, I wish I could erase this, but I'll use a new page. So we have V infinity far away, and this point has doublet and a vortex, and then you get some flow inside too. So if you draw the streamlines inside, I don't know, it'll be something like this, I suppose. I think it'll be like this, something like this. Okay, but essentially you're saying this cylinder is a streamline. The circle is a streamline, and so you can replace the circle with a wall, and that means the outside flow is the flow past a circular cylinder, but a flow that generates lift because of the asymmetry in the flow. Right, so now you have a cylinder that's generating lift. Now, how you get this is maybe of secondary importance, how you get this in practical life. So it turns out if you put a cylinder in a wind tunnel and spin it, you will get lift. But that's not exactly the same kind of flow as this. That comes due to viscous effects, because if the cylinder is spinning, the surface friction will cause also the flow to go faster on the upper surface than on the lower surface, kind of like this. So that comes due to viscous effects. This is completely potential flow. But the same general idea is what happens when you spin a cylinder in a real flow, like in a wind tunnel or water tunnel. So this has got non-zero lift, but zero drag. And the doublet strength is kappa and the vortex strength is gamma. So doublet strength will control the radius of the cylinder, and gamma is a circulation strength or vortex strength that will control the lift. So it turns out, without going into too much of the derivation, this lift that we generate here is related to V infinity, which is the free stream speed, and gamma. Let's just call it V for now. Okay. So V and gamma. Lift is related to V and gamma, and actually there's a theorem that connects all this called Kota-Joukowski theorem. And so Kota-Joukowski theorem states that lift per unit span is rho V cross gamma. So this V is the uniform velocity and gamma is the vortex strength. And if you take those as vectors, so this is the direction of V, which is in this direction. Gamma is into the page, and V cross gamma will give you a lift in this direction. And this is lift per unit span. Again, we are talking about 2D flows. So we see that L prime is perpendicular to V. So here we can write simply write L equals rho V gamma in this particular case, because V cross gamma is just V times gamma. Okay, so let's look at the flow past a cylinder for different values of gamma. So let's put first gamma equals 0. So when gamma equals 0, it's just flow past a circular cylinder with 0 lift, right? So you get symmetric flow and no lift. This is just, there's no vortex here. It's just a doublet and uniform flow and doublet. Right? This is what we looked at some time back. Now you add a little bit of gamma. Okay, so now from here, let's call this 1. Now we add a little bit of gamma, and we'll take the same cylinder. I'll try to draw it as much as possible the same as before. So gamma here is such that gamma over 4 pi V infinity is less than r. R is the radius of the cylinder. So if you put a small amount of gamma, you get a flow like this. So the stagnation streamlines might be here. Right, so initially in this flow, the stagnation streamlines are at the on the x-axis. When you put a small amount of circulation, the stagnation streamlines come here, and there's a certain amount of lift. This is number 2. So now let's increase the circulation until these two stagnation points come to the bottom here. And this will correspond to gamma over 4 pi V infinity equals R. So when you come to this value of gamma, when you keep on increasing gamma till it's 4 pi V infinity R, the stagnation points will coincide. If you go beyond this, the stagnation point will actually go off the surface. kind of interesting. I know I'm not super sure what practical application this has, but it's just as a sort of fluid mechanics solution. This is interesting to see. I think when you use conformal mapping to transform these flows, these become successively higher cambered airfoils, so there's probably some kind of a limiting value of the camber beyond which, you know, this is probably you probably can't transform it to realistic airfoil shape. So this Kutajakowski theorem that we talked about here, right? This is valid for lift equals rho v gamma. This is valid not only for circular cylinder, it's also valid for airfoils or any body. So this Kutajakowski theorem, I'm going to write it in short as KJ theorem, which states that L prime equals rho v cross gamma. This theorem is valid even for other shapes. So when we go to airfoils, we're going to see this soon, is when you go and look at the solution for lifting flow past an airfoil, so lifting flow, let's say the lift per unit span for this airfoil equals L prime. And then let's say V infinity is the free stream velocity, so that's the uniform flow. So now if you draw a contour around this airfoil, and you do, you calculate the circulation. Let's say this is contour A. So you say circulation for contour A, we'll call that gamma A, is integral around the closed contour A V dot dl. Right? That means you take this flow solution and you go to lots of points and you find V and you do V dot dl, dl going this way, and you do that integration, you'll get gamma A. Now it will turn out that the lift L prime will be rho V infinity gamma A. So this Kutajakowski theorem works even for airfoils, right? So we said rho V cross gamma. V and gamma are perpendicular, so it's just rho V gamma. That works even for an airfoil. On the other hand, if you go to, so if you take the full flow solution and you take a contour here, let's say this is contour B, and you do rho V gamma for this, this will be gamma B equals 0, because it doesn't envelop a lift producing body. That means if you take a contour around some object and you measure the circulation, if that circulation is non-zero, that means the body inside is producing lift when it's exposed to V infinity. And on the other hand, if you take a general contour with nothing inside, no body, nothing that's creating lift, that will automatically, or there's no vortex inside, then that gamma will be 0. Okay. So we are going to now connect all this with airfoils and kata condition, and very soon go to thin airfoil theory, like in the next class. So I'll stop here and see you on Thursday.